This is the key for the second portion of the final exam review material that you need for applied calculus. I'm going to walk you very quickly through these solutions. For the first one, we take a look at this graph over here for number 1, 2, and 3. This is the graph of the first derivative, not the function itself. And for each of these, the x value is 0, so we just look and see what's happening at 0 here. At 0, the value of the function is 4, which means the first derivative is 4 at x is 0. So we can cross off a and d because that's the function and d is the second derivative. We're working with the first derivative, so we know it's b or c. And what do we know about positive first derivatives? We know that the function is increasing at that value. We do not know anything about concavity with a first derivative, so we get to choose b. For the next one, it's asking for critical values. So you go over to the graph, you can do a number line chart, name it f prime, and then take each of the values that we have that we get a 0 for, and it's -0, -6, -3, -1, and 5. And when you look at these, what's listed here, you only have -6 listed, -3, -1, and 5 aren't listed, so you only get A. I'm sorry, this chart here is done for number 3. What's happening at x equals -6. So we've got the -6 here, and remember it is the first derivative, so what's happening to the left of -6, the first derivative is negative. What's happening to the right, the x values to the right, that first derivative is positive, which means that we have decreasing then increasing, so we have a relative min there at x is -6. The first one, we have a critical value that's neither a max or min. That's not true. We don't know whether it's an inflection point or not. We're not looking at the first or at the second derivative and concavity. So neither A nor B are true. That's C. We know that they both are not true, so we're going to choose C for number 3. For number 4, which of the following is a critical value? Critical values are when you take the function and take the first derivative of the function. So I see here I was rushing and doing this with another class. So let's go ahead and take the first derivative. So y prime is 2x minus 1. Critical values are when that is 0, 2x minus 1, and we solve that for x. Add 1 to both sides, divide by 2, you get 1/2. So the answer is E. So for number 4, the answer is E. For number 5, which of the following statements is true about this function? It's talking about minimum inflection points. So let's go take a derivative. The derivative of x cubed is 3x squared. Of -6, the next term is -12x. Of 12 is 0. So here's our first derivative. We can factor it. When you set it equal to 0, then we can find those critical values are 0 and 4. Do your number line, which is really our first derivative test, and we get increasing, decreasing, increasing. So we're seeing relative max, relative min. So what's happening here? It's saying there's a local minimum at 0, 12. But at 0, what we have is a maximum, so that one is not correct. There's a local minimum at 4, but what are we seeing here? Oh, there is a local minimum, but what's the y value at 4? When you substitute the y value of 4 up into here, you do not get 0, so we cross out C. Is there an inflection point there? Well, you can take the second derivative and check for concavity, and you're going to find that the answer here is D. Look at number 6, find the absolute max value. Here's our function, and we take the derivative, we get 8x minus 2. Find the critical value is 4. 4 is not on that interval from 1 to 2, which is where you're testing those absolute values, so we only use the endpoints 1 and 2. Substitute back into the original function, and that gives you a 15. Let's go ahead to number 7. For this one, you're supposed to be getting the derivatives of each of these functions, and do not simplify. Derivative of a log is 1 over what's inside. Chain rule out the derivative of what's inside, which is 2x plus 5, and you are done. For the next one, e to raise to anything, the derivative of that is keep it as it is. chain rule out the derivative of that exponent, which is 4x cubed minus 5. Derivative of the next term is 9x squared. The derivative of negative 17 is 0. So this is our unsimplified derivative. For the next one, it's an exponential, but the base is a number, not e. So when we take that derivative, we get the natural log of the base, which is 3. Keep it exactly as it is, and then chain rule out the derivative of that exponent, which is, for this piece, 16x cubed, for this piece, negative 4x. And for the next one, D, we've got a product here, so you're going to have to use the product rule. So we take the derivative of the first times the second, plus the first times the derivative of the second. It's a logarithm, so 1 over what's inside, chain rule out the derivative of what's inside. Look at number 8. When you look at number 8, let me look at the question, snappy suits. They're giving you price and cost. So here's price, here's cost that they give you. And revenue is going to be your price times your quantity. Simplify that. And then they're asking you for profit. Find a formula for revenue, find a formula for profit. Profit's revenue minus cost. Don't forget to distribute that negative sign. And then once you do that, you get this guy for profit. The last one, C, how many suits must be sold to maximize profit. And you use your calculator. You're going to have to do some messing around with the window because it's not very pretty to graph with this odd coefficient in front, which is 100th, and then a constant that's a negative 4,000. So you're going to have to adjust those max and mins for X and Y. So that is number 8. And, you know, I'm thinking, I said chain rule, and up here I had hesitated. Let me go back to number 7C. When you take the derivative of this and you're chain ruling out the derivative of that exponent, the derivative of that exponent gives you 16x cubed minus 4x. You do not chain rule out again. You just keep this guy as it is. That's what I wanted to mention, not to forget that, sorry. Let's go on to number 9. So given this function, they want you to use the first derivative test to find the extrema, then the second derivative test to verify it. So part A, first derivative, you take the derivative, factor it, and get those critical values. Don't forget the number line, which you need for the first derivative test. Test values to get whether they're increasing or decreasing. Here we get a relative max. Substitute that x value into the original function to get this y value. Here it's a relative min at 12, so take the 12, substitute it into the original function to get negative 1436, and that's your relative max or min. Remember, our answers always look like this: relative, name it, max or min, of, name the value, and then at whatever your x is, and then we have our relative min. We can use the second derivative test to check this, and the second derivative test does not have a number line chart. Instead, here's the first derivative from part A, take the second derivative of it. When you do that, then you substitute the critical values from the first derivative into your second derivative. And then if it is negative, that means it's got concavity down, so you have a relative max. If it's positive, which is what this is saying, then you have concavity up, which is a relative min. And substitute in to get the y value, so you get the same answer as above, which is what the goal was of that particular question. Now for part C, they're asking you for inflection points. This is where we use the sign chart for the second derivative. We already have this from part B. Set it equal to 0, find the critical value, put the critical value on the number line. Don't forget to label it as the second derivative. Do some test points. When you do, you find concave down, concave up, change in concavity, point of inflection. So you take that first critical and only critical value, put it into the original function, and get negative 750. So there's a point of inflection at negative 750. The last part of this question is asking you to find the absolute value of the given function on the interval negative 2 to 2. The critical values are negative 2 and 12. And from part A. Now 12 is not on this interval, so you're not going to use that value in this t-chart. Negative 2 is, but it's an endpoint. So that means that in this interval there are no other critical values. So the absolute max or min is going to occur at those endpoints. Substitute them into the original function, get the y values, and the smallest one is negative 64. That's the absolute max of negative 64 with that value. And then the other one is the absolute min at the other value. When you look at number 10, this is now doing multivariate functions, so it's asking you to evaluate f of 3, 1. So you just substitute the 3 in for the x, the 1 in for the y. That's a pretty basic one. For the next one, you're doing partial derivatives, just the first level, not higher order. And so with respect to x, holding y as a constant, e to the xy is a function of x, so we keep it as it is. Chain rule out the derivative of the exponent. The derivative of the exponent with respect to y, with respect to x is just y. Now some of you also put a 1 in front because the derivative of the x is just 1. It does not matter if you do that or not, it's okay. For this next piece, we're taking the derivative with respect to x. The y is a constant, it comes along for the ride. The derivative of natural log of x is 1 over x. You would chain rule out if what's inside had a derivative not equal to 1. This chain really, when you chain it, is just a 1. And then with respect to y, the first term is a function of y, so you get e to the xy. Then chain rule out the derivative of the exponent with respect to y, which is just x. And again, you could put times 1 and you put it in front or in back. Then the derivative of the second term with respect to y, the natural log of x is a constant. It comes along by itself. And then the derivative of the y is just 1. Sorry about the phone. Number 12 is higher order derivatives. So you want to take the derivative with respect to x, and then whatever you get, take it with respect to y. So let's take a look at this. With respect to x, this first term, you've got e to the 2y as a constant, comes along for the ride right here. E to the 2x, its derivative is e to the 2x. Chain rule out the derivative of the exponent, which is 2. And then the derivative of negative 2xy. The 2 and the y are constants. The derivative of the x is 1. Some people are putting a 1 there. And you get the exact same thing, 2 e to the 2x, e to the 2y minus 2y. Now, you want to simplify this because we have to take the derivative with respect to y now. So to do that, take a look at this first term. 2 is a constant. E to the 2y is a constant. We're taking, I'm sorry, I'm now reading my message on my phone. So, start again. We're taking the derivative with respect to y. The 2 is a constant, comes along for the ride. E to the 2x is a constant. It's sitting here too because both of those are just numbers. And then take the derivative of the e to the 2y. You write it as it is. Chain rule out the derivative of the exponent, which is just a 2. The derivative of negative 2y with respect to y is just the coefficient negative 2. Let's do part B. Now we're taking the derivative with respect to y, then with respect to x. So the first piece here with respect to y, the e to the 2x is a constant. It's got parentheses around here. E to the 2y, you write it as it is. Chain rule out the derivative of the exponent, which is 2. Then take that second term, negative 2xy. Take the derivative with respect to y as negative 2x. And then rewrite it to simplify because we need to take a higher order derivative. And let's take a look at this piece now and take the derivative with respect to x. The 2 and the e to the 2y are constants, so they get written in parentheses. And e to the 2x has a variable of x in it, so we write it as it is. Chain rule out the derivative of that exponent. Then minus 2x, take the derivative of that with respect to x, you just get minus 2. For number 13, we are moving into antiderivatives, and so this is asking you, if this is your derivative, what's your original function? So we add 1 to the exponent, divide by the new exponent. Don't forget the plus c. Let's go backwards by taking a derivative. The derivative of the constant is 0, which is good because it's not here. And the derivative of 2/7, x to the 7th, bring the 7 down. The 7 divides out with this, so you get 2x to the 6th, and that's exactly what we do that one first, because for number 14, what we need to do is use this initial value and actually find that c of the function. So we are given 2x squared minus x. We want the antiderivative, or the function for which this is its derivative. We get a whole family, which is why this c is here. Add 1 to the exponent to get cubed, so you get 2x cubed over 3. And for negative x, you get negative x squared over 2. So let's check it. Bring the 3 down. Divides out with this 3. So you get 2x squared. Yes. Bring the 2 down. You get negative 2x over 2, which is just negative x, because the 2's divide out. That works. Don't forget the c. Now, in this step, we're going to use that initial value they gave us, where x is equal to 1 and y is equal to negative 3. With that, that gives us negative 3 is equal to 2, 1 cubed over 3 minus 1 squared over 2 plus that c. Go ahead and apply the exponents, add these fractions, then add that fraction to the other side, and you get this constant. So we go back up here to our function, keep those first 2 terms, they're right here, then take that c and substitute in the value of c that you found. Remember, this question is asking you for the function. It's not asking you for c. You have to find the c, but only so that you can put it back into this function again. Okay, number 15. Now we are using calculus to do integrals, and we rewrite whenever we can. For this one, we write x to the negative 5. Then we add 1 to the exponent, divide by the new exponent. Just don't forget the c. And you can rewrite it like this, or you could leave it like this. Both are correct. For this one, what function has a derivative of 1 over x? And that is the natural log of x. Remember, we are assuming that x is positive when we've got it inside a logarithm. Don't forget the c. For 17, what function has a derivative of e to the x? It's e to the x. The 2 comes along for the ride. Check it. What's the derivative of 2e to the x? 2e to the x. So we're right. Derivative of a constant is 0. When you look at number 18, I went ahead and rewrote it. When I wrote it down on here, this had the square root of x, but you rewrite it with an exponent. Each of these is using different rules that we know. For this first one, we add 1 to the exponent, divide by the new exponent to get 4/3 x cubed. For this one, we have e raised to a function, which is 4 to the x. So we get negative 3, e 4 to the x, and then to come backwards, we would multiply by the chain rule to get a 4. So we have to get rid of the 4, and so we divide by that. For the next one, again, it works just like that first one does. For number 19, this one now is a definite integral. This one is an indefinite integral. There are no bounds on it. You get a function with a c. When you're done, these have bounds on them. With bounds on them, that means you're going to get a number, because it is doing the area under the curve that they give you here between these two x values. So what function has a derivative of e to the x? It's e to the x. Write your lower and upper bounds here. Substitute the upper bound in, e to the 3rd. The lower bound, e to the negative 1. Notice no c. That's your answer. Don't approximate it. For 7, what function has a derivative of 7x? It's just 7. So this guy works backwards, sorry. Substitute the 3 in to get 21. 21 here, and then minus 1 in there, so you get minus 7, which is a negative here then. To give you positive, you get 28. For number 21, 4 minus x, what function has a derivative of this? You get 4x minus x squared over 2. I know we're rolling at this point. Put the bounds in, substitute the upper bound in, the lower bound in, watch the signs, and then subtract. Remember, you can use your graphing calculator and second calc 7 for the integral, hit the bounds, and check your numbers to make sure your calculations are correct. Yes, you need to show this. Yes, you need to show those bounds. Yes, you need to show it substituted in, and then give a final answer. For number 22, find the area under the curve. y equals 4x cubed on the interval 0 to 3. That's what this definite integral is doing, and we're asked to evaluate it. So this is just like the previous problems, only we had to set up the integral. For number 23, find the area of the region bounded by these two curves. First thing you have to do is set them equal to each other to get the intersection points, which is 0 to 2. Then you should graph it, because you need to know which function is the upper function. It's always upper function minus lower function, and you subtract that lower one from it, watch the signs, simplify it. Now you're right back to where we were again just a minute ago, and you run those numbers and get a 4. And the last question, number 24, is average value. And the average value over the interval of 0 to 3. So here's 0 and 3. Upper and lower, upper, lower. So it's 1 over the upper minus the lower. Then write your integral. Go ahead and find the antiderivative. This is 1/3. Notice it stays outside. Substitute the 3 in. You get this. Substitute a 0 in. You get this. Simplify that to get 9. 1/3 of 9 is 3. So that's it. Hope you're having a great day.